Welcome back everyone. In this final lecture, I am going to state the very important result in representation theory of finite semi-simple algebras, which is called BGG resolution. So, this is indeed very important result proved in this representation theory. So, this actually like character formula can be thought of as an immediate corollary of this BGG resolution. So, even to understand this BGG resolution, we need to actually understand so what is like filtration and then filtration by some particular by Verma modules and so on. So, let me actually like state it in a much simpler way using this long exact sequences. So, then it will become actually very clear. So, before stating this BGG resolution, let us first prove some important result in for Verma modules, then we will be able to state this BGG resolution. So, let us actually start with lambda being dominant, because we are not going to be interested in other weights. So, take lambda to be dominant weight. So, again you can actually fix G to be SLN or SLN plus 1, whatever you want. So, if you take G being SLN, lambda being dominant, then one can actually look at the corresponding Verma module. So, this is the Verma module. So, we know that for dominant weights, the irreducible module is indeed a quotient of the Verma module. So, this is something we know. So, what we want to understand, what will be the kernel of this map. So, this is the quotient. The kernel of this map we want to understand very explicitly, and the kernel is indeed going to tell you like what will be the term in the second term in the BGG resolution. Okay. So, for that purpose, let us just outline, because the proof already we have seen. So, the proof of that whenever lambda being dominant implies V of lambda is finite dimensional, the same proof can be adopted here and then prove the following. If you take this kernel pi, one can claim that this kernel pi is indeed the submodule generated by these elements yi power lambda of hi plus 1 v lambda for all I from, let us say, I will denote the indexing set to be I, which is 1 to n minus 1 in this case. So, recall lambda of hi, they are nothing but the omega ith coefficient in lambda, and yi is nothing but generator of this C. Okay, yi is nothing but G minus alpha I, the generator of that. So, this is indeed proved as follows. So, if you call this module L of lambda, which is m of lambda modulo this kernel pi, then you can easily see that this is actually surjects on, there is an induced map that surjects on V of lambda. So, now the claim is this L of lambda is a finite dimensional highest weight module. Note that if we take for example, the generator of V lambda, generator of this m of lambda and then descend to this kernel pi. So, let us call the generator to be W lambda for m lambda. So, m lambda is generated by this W lambda, which is also n minus generator. So, then we can look at this W lambda plus kernel pi. So, this is going to be generator, cyclic generator for this L of lambda, because L of lambda is just a quotient of M of lambda. So, now you can easily see that this vector is indeed highest weight vector. So, it is that says that L of lambda must be highest weight representation. So, this is indeed highest weight representation, that is easy to see, because this is being quotient of M of lambda, that is all. So, now you have this if you call this vector V, then Fi power lambda of Hi plus 1 V is indeed 0, and this is 0 for all I range from 1 to n minus 1. So, which is exactly I, the indexing set. So, now because this W lambda already satisfy the following relation, H W lambda is given by lambda of H W lambda, and X W lambda is 0 for all x in n plus. So, this implies that we have this following relations for V. H V is lambda of H V. So, that means V lies inside this L of lambda lambda, lambda weight space, and then X V is 0 for all x in n plus. Okay. So, this forces that V is highest weight vector for this L of lambda, and moreover we also have these relations coming from this module. So, Fi of Yi of, so I called it as Yi. So, let us stick with the notation. So, Yi of lambda of Hi plus 1 V is 0, and for all I in I. So, these relations are true there in L of lambda. So, now if you closely go through the proof of that we provided for V of lambda being finite dimensional for lambda dominant weight. So, because V of lambda defined to be the unique irreducible quotient of M of lambda, if you go with that definition, then we proved a theorem that tells that V of lambda is finite dimensional for lambda dominant. So, that actually tells you that similar proof will tell you that with these relations, so we will have L of lambda finite dimensional. Now, if L of lambda being highest weight representation and finite dimensional, so now using complete reducibility, you can easily see that L of lambda can be written as a direct sum of irreducible representation. So, L of lambda you can write it as M1 direct sum etc. direct sum Mk, where Mi's are all irreducible. So, this is just Weil's theorem, Weil's complete reducibility. So, now you can easily see that if you take this L of lambda and then look at the lambda weight space, which is the highest weight. So, then this will be M1 lambda direct sum etc. direct sum Mk of lambda, but this is actually it is not hard to prove. This is the dimension of this L of lambda lambda is exactly 1. So, that forces that this, let us say without loss of generality, M1 lambda is being non-zero, then that would imply that this entire V must lie inside M1 lambda, and that would force that L of lambda is subset of M1, that would force that L of lambda is equal to M1. So, that forces that L of lambda is irreducible, and that implies L of lambda is equal to V of lambda, because V of lambda is the only irreducible quotient of this M of lambda. So, this proves that if you go modulo this kernel, which is a submodule generated by this Yi power lambda of Hi plus 1 V W lambda. So, that is going to be exactly, so let us call this as W lambda. So, this is exactly V of lambda. So, indeed we have the following exact sequence. So, we have M of lambda, and then we have this V of lambda, and then we have this direct sum of these submodules. Okay, so let's first of all, like before writing that direct sum, let's write it as exact sequence, which is the submodule generated by this UG yi power lambda of hi plus 1 w lambda, where I ranges from 1 to n. So now, if you look at this UG module generated by this yi power lambda of hi plus 1 w lambda. So, you can prove that. I will leave it as exercise, because this is happening inside the Verma module, and the weight of this. So, you can easily see that the weight of this vector yi lambda of hi plus 1 w lambda is going to be lambda minus lambda of hi plus 1 times alpha I. Okay, so what is Si of lambda plus rho? So it's going to be lambda plus rho minus lambda plus rho of hi alpha I. But note that rho of hi is being 1, that tells you that Si of lambda plus rho is nothing but lambda plus rho minus lambda of hi plus 1 alpha I. So, the difference between this element and this element, you can see that addition of rho. So, that is what actually gives you what is called the dot action. So, the dot action on this lambda plus rho is, or on the lambda itself, is defined to be lambda Si of lambda plus rho minus rho. So, this is how one defines this dot action. So, just a shorter notation. So, if you use this dot action, then you can easily see that. So, this submodule generated by yi power lambda of hi plus 1 w lambda is isomorphic to the Verma module m of Si dot lambda. Okay. And this is easy to prove, because you just need to prove that there is a surjection from m of Si dot lambda to m of lambda, and that is given by this sending the generator to this whatever the generator here, you send it to this yi power lambda of hi plus 1 w lambda, and any non-zero map from one Verma model to another Verma model will be injective. So, that just follows from the fact that Verma models do not have any like the universal empirical algebra has no non-zero devices. So, now using that, you can prove that this is indeed injective map. So, this module becomes isomorphic to this m of Si circle lambda. So, now so I will leave this also exercise. If you have a map from m of lambda 1 to m of lambda 2 is a non-zero map, then that implies, let us see, call it F. F is injective. Okay. So, now using this, you can prove that this map is indeed isomorphism for these two modules. So, now if you go back to the exact sequence that we have, so this you can replace by the direct sum and then see what happens. Okay. So, this is giving you direct sum of m of Si dot lambda for I range from 1 to n to m of lambda to v lambda, and then we have this. Okay. So, this m of lambda, they are treated as free objects in the category of that one can define called BGG category. So, then we have started actually building this resolution. So, now this is nothing but sum of free modules. So, now now you can easily see that, so this is indeed projective resolution, not free resolution. So now where this actually kind of ends, that is what you have to see. So so it's not very hard to see, this map is never injective. So this map will have some kernel, okay, this map will have some kernel, call this is pi 1, this is pi. So then the kernel of pi 1, and then with that we can complete this to exact sequence. So basically BGG resolution indeed tells you, so what is that exact resolution. So indeed let me state this result. So for that purpose, let us first define this while group action. So while group being Sn minus 1. So given W in the while group, the W dot lambda. So lambda, let us say some element of H star. So then W dot lambda defined to be W of lambda plus rho minus rho. So this is how you define the dot action. So now using this dot action, you can see that, so here is the theorem. So this is proved by Bernstein, Gelfand and Gelfand. Bernstein, Gelfand and Gelfand. So this resolution indeed says, so we have this following log exact sequence. So let lambda be in dominant, and we have a long exact sequence of G modules. So how the resolution is given? So it starts with V lambda, and the second term being m of lambda, and the third term being direct sum of m of Si dot product lambda for I ranging from 1 to n. Then the fourth term, so this resolution goes by the length of W's. So basically you take, so these Si's can be treated as length 1 elements. So length of W is 1 if and only if W equal to Si for some I. So using this observation, the fourth term is going to be m of W dot product with lambda, where W comes from W whose length is being just 2. So then you continue this as an exact sequence. So for example, the kth term, so this is going to be m of W dot product lambda, where W comes from W whose length is exactly k. And it is a fact that one can actually verify easily for any while group, in particularly for the symmetric group. So you have something called longest element, and that element is unique. If you go with this length function, you can find an element that has longest length, okay, and that element must be unique. And so that this resolution continues, and then it ends with this m of that longest element is denoted by W naught lambda, and then we have this exact sequence. So this W naught is the longest element in the while group W. Okay. So we have this very explicit exact sequence of G modules, and this is indeed actually happening in the category BGG. So you can easily see that the modules that are involved in this resolution, except this V lambda, everything else is actually infinite dimensional modules. So you have to enlarge the category. So you embed this finite dimensional category. So let us call it category of finite dimensional is denoted by usually C finite. So this you can actually treat it as sitting inside BGG. So I am not going to get into the definition of BGG, but BGG is something like it has a filtration, let us say given by like these highest weight representation, that is Verma modules, finite filtrations with the highest weight representation. So, now we have this long exact sequence. So, now one can actually reinterpret this wild character formula as follows. So, you look at this chi lambda is given by S lambda plus rho divided by S rho. So, by definition of S rho, you can easily see that this is going to be summation the sine of W sorry e power W lambda plus rho W in W, and then divided by, you can write it as S rho. So, what is this S rho? S rho is given by summation sine of W e power W rho W in W, which is also given by e power rho times product 1 minus e power minus alpha, alpha coming from delta plus. So, if you think about it, so the u n minus, so the h character of u n minus is exactly given by this 1 divided by product 1 minus e power minus alpha, alpha in delta plus. Since m of lambda is isomorphic to u n minus as h module. So, you can see that the character of m of lambda, because it actually has the highest weight lambda. So, this is indeed given by e power lambda divided by product 1 minus e power minus alpha, alpha in delta plus. So, if you actually take now this dot action, okay, so let us rewrite this chi lambda again. So, this chi lambda now we can rewrite as follows. So, chi lambda equal to summation sine W e power W lambda plus rho divided by this product 1 minus e power minus alpha, alpha in delta plus, and then e power. So, this e power rho is there, yeah, we have to write this here where W in W. So, now you can actually bring this e power rho above, and then you can see that. So, this is going to be sine of W e power W lambda plus rho minus rho divided by the product 1 minus e power minus alpha, alpha in delta plus, where W in W. So, now what we can do, we can actually just rewrite this as using the length function, where the length is starting from 0 to infinity. It is, even though finite sum, just write it as infinite sum, not a problem. So, then you can easily see that this is going to be those W in W, where the length of W is being exactly k. So, then this minus power k will come times. So, you have the sine is becoming, okay, sine of W is nothing but minus 1 power length of W. This is something I already left it as exercise. So, now if you use that, you can see that this is going to be exactly summation W in W, length of W equal to k times e power W dot lambda, because W dot lambda is nothing but W of lambda plus rho minus rho divided by this product 1 minus e power minus alpha, alpha in delta plus. So, that means this is exactly equal to summation minus 1 power k summation W in W, length of W equal to k, the character of the Verma module corresponding to this dot action W dot lambda, where k ranging from 0 to infinity. Okay. But if you think about it, that is the sum that we have as the in the BGG resolution. So, this is the term that we have in the BGG resolution that has the character exactly the summation character of m of w dot lambda w in w length of w equal to k. Now, since this is exact sequence, now the character of v lambda can be written as alternating sum of these things. So, now that alternating sum is exactly given by this sign minus 1 power k. So, now you can see that. So, if you reinterpret chi lambda in terms of these characters of this Verma modules, then the BGG resolution immediately tells you that this character of chi lambda is exactly the sum of these character of the Verma module that are involved there. Okay, this is indeed follows from the following exercise. Maybe I will state the exercise and then stop. If you have this sequence of Verma modules, okay, sorry, the sequence of G modules, let us say V1, V0, 0, V2 and so on, some let us say Vm. So, let us say this is exact sequence of G modules, even H modules are enough. So, this is exact long exact sequence of H, let us say weight modules. So, that means each Vi is H weight module. So, that means Vi can be written as direct sum of H weight spaces with finite dimensional weight spaces. So, then the character of Vi makes sense. Okay. So, now if you have such an exact sequence, then you can easily prove that this same sequence is indeed gives you sequence at the level of muth weight space for each mu. So, if this is what you have, then you can prove that at the muth weight space for any mu you have the following exact sequence. And using this you can easily prove that the character of V naught is going to be character of V1 minus, so this k is being, so k actually should be greater than or equal to 1. So, if the length is 0, then it is going to be exactly e power lambda. So, which corresponds to m lambda. Okay, that is fine. So, this is there is no issue here. So, this corresponds to length 0 and then everything else is there. Okay. But the length 0 thing should have positive sign, that is what we wanted. So, okay, k 0 it becomes positive. So, then this is summation minus 1 power I plus 1 I greater than or equal to 1 character of Vi. So, maybe it is good to start with V minus 1, then it will become exactly what we had before. So, this is let us say minus 1, this is 1, this is sorry, this is 0. So, this is 1 and then all the way to length m. So, then you have V 0 mu, V minus 1 mu 0. So, then you write character of V minus 1 as I greater than or equal to 0 minus 1 power I character of Vi. So, now using this simple exercise, you can easily see that so this identity is true from BGG resolution. Okay, so with this I am actually stopping this course due to time constraint. I hope all of you must have enjoyed this course and then learned some representation theory. So, I hope you will actually continue to do work on representation theory in the future. So, I wish you all the best for your future endowments. Okay, I will stop here. Thank you.